Today in honors chemistry, we want to talk about quantum numbers, but before we do so, I'd like to go back and type a few loose ends on electron configuration. So the other day in the video, I went through neon, so electron configuration, and then in honors, I had two more things at the bottom, which are ions. So let's talk about that real quick. So sodium, if you have your periodic table handy, sodium has 11 protons, therefore it has 11 electrons. If it gets rid of an electron, it will have 10. So when it gets rid of an electron, it becomes Na+. So when you do its electron configuration, it will be identical to neon's because it lost that electron, so it has 10. It would give it 8 in its outer shell. So sodium ion would be 1s2, 2s2, 2p6. So your metals will always give up electrons and become positive. Either they'll have a 1+, 2+, or 3+ charge. The next example was sulfur, sulfur 2-. So sulfur normally has 16 electrons. It would have 6 in its outer shell. And so atoms like to achieve 8 in their outer shell. So if sulfur could gain 2 electrons, it would fill its outer shell and it would become the sulfide ion. And so instead of having 16 total electrons, it's going to have 18 total. So its electron configuration for the S2- is 1s2, 2s2, 2p6, 3s2, 3p6. So once again, you can add up your superscripts, 6, 7, 8, 14, 15, 16, 17, 18. So it has 18 electrons. Your nonmetals, if you put them with the metal, they tend to gain electrons, so they can gain anywhere from 1 to 3 electrons and develop a 1-, 2-, or 3- charge. Okay, and then the next thing that was not on the video, it was, it talks about, in your notes, it talks about transition metals. And I didn't address that in the video. So transition metals will give up their outer shell electrons first, and these are their s electrons when forming ions, okay? So up here we did silver, we did its actual, or we said its expected was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, this should be 4s2, 3d10, 4p6, 5s1, 4d9. And then we said that if they can get their D shell half full or full, that makes them more energetically stable. And so one of the S's will move to the D. I've got to correct this real quick. Okay, so silver's actual is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, because 1 moves out of the S into the D, and now the D is full, 4d10, okay? Now, if you have the silver ion, it has a plus charge, so that means it lost an electron. And so even though when we say the electron configuration at the end is 5s1, 4d10, 4d is higher energy than 5s, but the 5s, the fifth energy level, is on the outside of the 4d. And so it's going to give up this S electron before it would lose a D. And so silver ion would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then 4d10. So it got rid of this 5s1. It emptied out the 5th energy level and did not take any from the D. Okay. Copper's expected was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. So once again, if it can get its D half full or full, it's more, it's at a lower potential energy, and so one of the electrons moves out of the 4th energy level in the S sublevel to fill the D. So its actual is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Well, the copper 2+ ion simply means that copper lost 2 electrons, okay? So what it's going to do is it's going to lose this 1 in the 5th energy level. So that energy level is empty. And then it's going to lose 1 in the D. Okay? So the copper 2 plus ion is 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Keep in mind that the 4th energy level is empty, and we needed another electron, so it came out of the 3d. Okay? All right, and so now we are ready to address quantum numbers. So you'll probably want your periodic table handy. We're probably going to write on it some more. Okay. So every electron in an element has an address of 4 quantum numbers. And we talked about those a little bit earlier on, but let's write them down. So your 4 quantum numbers are N, L, M sub L, and then M sub S. So we're going to talk about what each of those means in a little bit more detail. According to Pauli's exclusion principle, no 2 electrons in an atom can have the same set of 4 quantum numbers. They can have up to 3 in common, but they will not have 4 in common, because then you'd be talking about the same atom in that, that same electron in that atom. So N is the main energy level, or the principal quantum number. It describes the size of the cloud. So as you add more and more energy levels, the cloud gets larger. It can have values of anywhere from 1 to 7 for the known elements. Okay. L is called the angular, A-N-G-U-L-A-R, momentum quantum number, or the azimuthal, A-Z-I-M-U-T-H-A-L, quantum number. And it's talking about the sublevel, and your values can range anywhere from n-1 to 0. So your L value can never be the same as an N. It has to always be at least 1 less. And it's going to describe the shape of the cloud. So remember, if it's S, it's spherical, P is peanut or dumbbell, D is clover. Okay, so on your table, so from the other day, this is your S block. This is your P block. This is your D block. And this is your F block. Okay? If an electron is in the S block, its L value is going to be 0. If it's in the P block, its L value is going to be 1. If it's in the D block, its L value is going to be 2. And if it's in the F block, its L value would be 3. Okay. So we're going to go back and put that in. So S is going to be 0. P is going to be 1. D is going to be 2. And F is going to be 3. Okay, our next quantum number is M sub L. M sub L stands for the magnetic quantum number. And it describes the orientation of the orbital in space. So what axis is it on? It can have values anywhere from a negative L value to a positive L value. And so this is where it's helpful to draw out your orbital diagram. And we'll do that in a second when we talk about some of these. Okay, so the S has only one orbital, so its M sub L is 0. So it only has one orbital, and it's a 0. P has 3 orbitals. So what I do is I always, over to the side, just draw 3 orbitals. The center one is going to be 0. The one to the left is a -1. The one to the right is a +1. So it can have values of anywhere from a -1, a 0, a +1. So with your m sub L value, you need to give a plus or minus sign unless it's a 0. Your D has 5 orbitals. So once again, over to the side, I draw my 5. 1, 2, 3, 4, 5. The center one is 0. Heading to the left, it's minus 1, minus 2. Going to the right is plus 1, plus 2. And this comes helpful when we start placing electrons so you can see what the m sub L number is. So it can have values of anywhere from a minus 2, minus 1, 0, plus 1, plus 2. F has 7 orbitals, so I'll draw you 7 orbitals. 1, 2, 3, 4, 5, 6, 7. The center is 0. Going to the left is minus 1, minus 2, minus 3, plus 1, plus 2, plus 3. So its values can be anywhere from minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Okay? M sub S is the spin quantum number. It only has 2 possible values, a plus 1/2 and a minus 1/2. So once again, on the M sub S, you must give it a plus or minus. Okay? Each orbital can hold 2 electrons, but if it does, they have to have opposite spin or spins. Since spinning charged particles create a magnetic field, the electrons must spin in opposite direction, and the reason they do that is it reduces repulsion. So, or we'll just say minimizes. Minimizes. Okay? Okay, so our first problem is give the quantum numbers for the 6 electrons of carbon. So if I were you, I'd put this on pause in a second. List your quantum numbers at the top. N, L, M sub L, M sub S. Go ahead and number 1 through 6 to represent the 6 electrons of carbon. Okay, so with your periodic table close to where you can see it, so carbon's first electron, if it's its first electron, we know it's going to be in the first energy level, so its N is 1. Its L, well, it's in the S block, and so L is automatically 0. If L is 0, M sub L can only be 0. And over here, I'm going to draw my orbitals, and so there's my 0 orbital. We're going to put our first electron up. If it's up, we say it has a plus 1/2 charge, or 1/2. It's a plus 1/2 spin. Okay. Its second electron, so bring helium over here because that's what carbon's second electron is going to look like. So it's still in the first energy level. So its N is 1. You're still going to be in the S block. So your L is 0. So therefore your M sub L has to be 0. And now it's got a second electron. And so we're going to put that electron going down. So its M sub S is a minus 1/2. Okay? Its third electron. So its third electron is going to be in the second energy level. So its N is 2. Since you're in the S block, its L is still 0, so its M sub L has to be 0. And it's going to be the first electron. And so its arrow's pointing up, so it is a plus 1/2. Okay. Its fourth electron is going to go into the second energy level. Okay, so its N is 2. Its L is still 0 because it's in the S block, so M sub L has to be 0. And now that arrow is going to go down, so it is a minus 1/2. So they can share up to 3 of the same quantum numbers, but they cannot have 4 of the same quantum numbers. Okay, its fifth electron. Its fifth electron is still in the second energy level, so its N is 2. Now we're going to be in the P block, so your L value for a P block is 1. Now we're going to draw our 3 P orbitals over to the side, 0 in the middle, minus 1, plus 1. And so it is its fifth electron, so it's the very first one in the P. so its M sub L is -1, and the arrow is pointing up, so it is a +1/2. Its sixth electron is still going to be in the second energy level, so its N is 2. We're still in the L block, so it's, we're still in the P block, so its L is 1. And now it's the second electron, so you do not pair up electrons until you've given each of the P's 1 because they're degenerate. So it goes, that electron goes in the 0, so its M sub L is 0. It's pointing up, so it is +1/2. So this would represent the quantum numbers for the 6 electrons of carbon. Okay, the next one says give the quantum numbers for the first P electron of silicon. So we're here in silicon, and this is your first P, okay? So we know we're in the third energy level, so our N is 3. I'm just going to use this up here and line them up under here. We're in the P block, so our L is 1. Okay. We have 3 P orbitals, 0, -1, +1. It is your first P, so that's your first P. And so your M sub L is a -1, and the arrow's pointing up, so your M sub S is a +1/2. Okay. And then the next question says give the quantum numbers for the second 3P of silicon. So we know it's still in the third energy level, so your N is 3. We're in the P blocks, your L is 1. And it's the second P electron, so we're talking about this one right here. So it is in the 0, so its M sub L is 0, and it's pointing up, so it is a +1/2. Okay? So keep in mind, once again, your M sub L must have a plus or minus unless it is in the 0, and your M sub S always must have a plus or minus. You don't give plus or minuses to your N or your L. Okay, give the quantum numbers for hydrogen. Well, hydrogen's super simple because it only has 1 electron, and so its N is going to be 1. It's going to be in the S block, and it's going to be, so your M sub L has to be 0, and it's going to be pointing up, so it's a +1/2. So it's identical to what? Carbon's first one. Okay. Okay, the next question says, would this be a valid set of quantum numbers? 4, 4, 0, -1/2? No, it would not, because your L can never be equal to your N. It always has to be at least 1 less. Okay. What about this? 3, -2, +1, +1/2? No, it is not valid because your L is just, it could be 2, but it's not going to be a -2. Okay. Okay, so that finishes it up for this chapter. Thank you, and now you can finish up your set 3.